All right, welcome to the Explainer. Today, we are going to pull back the curtain on generative AI, to really see the engine that's chugging away behind all that magic. I mean, we've all seen the incredible things these tools can do, right? You get these stunning images, complex code, and it all just comes from a few words and a text prompt. So, how in the world does a computer go from just a handful of words to a work of art? Well, here's the thing. It's not some unknowable magic. It's actually a super fascinating story about math and some seriously clever engineering. Yeah, as this guide puts it so well, all that surface level magic, it's standing on a deep bedrock of math and engineering. And the best part is, the concepts are surprisingly understandable. So let's do it. Let's peel back that surface layer and really look at the mathematical engine that powers the whole thing. Okay, so to get how AI thinks, we first have to get a handle on its language. And believe it or not, that language is basically rooted in three core areas of math. So first up, we've got linear algebra. Now, what this does is it gives the AI a way to see relationships. It basically turns, well, everything, words, pictures, even abstract ideas, into a set of coordinates on this huge, multi-dimensional map. Think of it this way. It's how an AI just knows that the word cat is way closer to kitten on that map than it is to, say, car. And this is where it gets really cool. The distance and the direction between these points on the map, they actually mean something. This lets the AI reason by analogy, just using simple math. It's literally how it can figure out that if you take the vector for king, subtract the vector for man, and then add the vector for woman, you land almost perfectly on the vector for queen. Wild, right? Okay, next up, calculus. This is the engine for learning. See, models get better through something called gradient descent. You can think of it like trial and error, but on an absolutely massive scale. Just picture a ball rolling down a valley. It's always going to find the steepest path down to get to the very bottom, right? Well, the AI does exactly that. It's always taking a tiny step in whichever direction reduces its errors the most. And finally, there's probability and statistics. This is what lets these models handle uncertainty. By just gobbling up enormous amounts of data, they get so good at spotting the underlying patterns that they can start generating brand new things. A sentence, a snippet of code, a picture, that look like they could have been in the original data set. So there you have it. Those are the core ingredients, the math that makes this whole thing possible. But now that we have the building blocks, let's look at the actual recipes. We're going to see how different AI architectures popped up over time, each one designed to solve a totally new kind of creative problem. Man, the last decade has been an absolute whirlwind. I mean, we've seen this lightning-fast evolution from kind of blurry, abstract images to things that look hyper-realistic, and then way beyond. And the thing is, each new model is literally standing on the shoulders of the giants that came right before it. The early models, they had some serious trade-offs. You had VAEs, which were pretty good at understanding the structure of data, but honestly, the images they made were often kind of blurry. But then GANs showed up, and they solved this with this brilliant two-player game. You have one AI, the forger, trying its best to create realistic images, and a second AI, the detective, whose only job is to spot the fakes. This constant competition led to incredibly sharp images, though, the process itself could be a little unstable sometimes. And then came the diffusion models, which really gave us the best of both worlds. They work by learning this really peculiar skill. They learn how to perfectly reverse the process of an image just dissolving into random staticky noise. So by getting incredibly good at denoising, they basically learn how to create a complete masterpiece from what starts as pure static. It's an amazing idea. But the real earthquake, the thing that changed everything, was the transformer architecture. Its key innovation is something called the attention mechanism. And what it does is it lets a model look at an entire sentence all at once, weighing how important every single word is to every other word in that sentence. This ability to deeply understand context, well, that's the engine humming inside tools like ChatGPT. So that brings us right up to the modern large language model, or LLM. And you gotta understand, training one of these isn't really like programming. It's more like raising a digital brain through this massive three-stage industrial scale process. Okay, so phase one is pre-training. This is where the model basically reads a huge chunk of the internet to learn, well, everything. Language, facts, how to reason. Then you have supervised fine-tuning. Here, it's taught how to be a helpful assistant by showing it tons of high-quality examples of questions and answers. And finally, you get to the most crucial part, alignment. This is where actual human reviewers rate the AI's responses, which teaches it how to be helpful, harmless, and, reliable. And this whole process led to a really key discovery, sometimes called the chinchilla insight. And it's this: size isn't everything. Researchers figured out that the secret to a better model wasn't just making it bigger and bigger. It was about feeding a smaller model more high-quality data. It turns out the amount and quality of that data is just as vital as the sheer number of parameters in the model. All right, so now we have this incredibly powerful pre-trained model, but it has one huge weakness, a really critical flaw. Let's dig into what that is and how engineers get around it to make these things truly useful in the real world. Yeah, here's the crucial point. A model like GPT-4 is basically frozen in time. Its knowledge has a cutoff date. It knows absolutely nothing about anything that happened after its training was finished. So how do you get it to talk about what happened in the news last week or analyze your company's private financial report from yesterday? Well, the solution is this really clever system called retrieval augmented generation, or RAG for short. The best way to think about it is like giving the AI an open book test. So instead of trying to rely on its frozen memory, the system first goes out and finds the most relevant, up-to-date information from a knowledge base. Then it hands that info to the AI and says, okay, using this, craft the perfect answer. It's a game changer. And this very ability, the power to connect these models to external live data and tools, is what's pushing us beyond just building bigger models. It's launching us into an entirely new era of AI systems. So we're now starting to move from just simple chatbots to what people are calling AI agents. And this is a huge leap. We're not just talking about systems that can answer your questions anymore. We're talking about systems that can reason, they can plan, and they can actually take actions in the digital world to get a complex job done. Something like researching and booking an entire vacation for you or managing your email inbox while you're out of office. So, what this really all means is that the frontier of AI is shifting right under our feet. The race isn't just about who can build the biggest, baddest model anymore. It's about who can build the smartest systems that use these incredible models as their core brain or their reasoning engine. And this big transition leaves us with a really critical question for the future, doesn't it? As these AI systems become more and more autonomous, more capable of actually acting in the world, the great challenge is no longer just making them more powerful. The real challenge is making sure their goals and their actions stay perfectly, and I mean perfectly, aligned with our own.